Nothing means anything without our brains. Not science, not religion, not politics, not love. Without our brains, nothing. Zero. Everything we know and do, all the sense of human thought, all the feelings of human emotion, all the questions of human existence, all are the product of the brains in our heads. Thought, emotion, existence, what's it all about? I could start with physics, philosophy, psychology, religion. I do start with the human brain. How do human brains think and feel? I'm Robert Lawrence Kuhn, and Closer to Truth is my journey to find out. My search begins in my hometown, New York, on the East River in Manhattan, at the NYU Medical Center, where I meet the Department Chair of Physiology and Neuroscience, Rodolfo Llinas. Rodolfo's a visionary and a scientist, all his life wondering about the brain.
Of all our organs, the brain is the most spectacular from many points of view. If you consider about 1.5 liters, about 3 pounds, our body is 150 pounds. So it's about 2% of the weight.
Right.
It requires 25% of all the energy. How did it came to be? What do we need brains for? What is it that they do that make them so special? The brain evolved to be able to move in an intelligent fashion. First of all, if you're going to move, it's going to cost an enormous amount of energy.
Yes.
So it means what? It means you have to be able to eat other animals.
Yeah, to get
because
that energy.
You cannot get enough energy from the sun. And people don't realize the advantage of being able to flee from problems, to run away. In order to do that, you require to have joints and muscles and so on. Secondly, you need to have a desire to move. You could imagine an animal that could move but doesn't want to move, so an intentionality. In order to have intentionality, you have to have the ability to predict. You don't want to move into danger. So I consider these to be the 3 basic issues about how the brains are about. Movement, intentionality, to begin to, and then prediction. As far as I'm concerned, that's all there is. That's all you need, in fact.
And so thinking, as we define thinking in this magical, mystical thing, is really what?
Thinking is a premotor event. Thinking is internalized movement. Thinking is all the things that you could do, out of which one you will do. That is what thinking is about. We are emulating reality inside our head. We have managed to generate a dream-like condition where we actually have sounds and objects that move with respect to backgrounds and all of these things without effort. So that is basically what the nervous system is about. It's a beautiful device to emulate reality. And so in fact, even when we are awake, when we're deriving an equation, when we are thinking of a theory, when we are contemplating what we are about to write, this music is inside. You are actively dreaming, although you are awake.
Yeah.
So in fact, this is mostly what we do.
Movement, intentionality, predicting. According to Rodolfo, that's what the brain does. All else is derived from these, he says. All the expressions of human personality, all the flourishings of human civilization come from movement, intentionality, predicting.
So we're just adding some electrolyte gel here to your scalp.
But how does the brain do it? Can we look inside a living brain? We surely can. And to find out how, I fly out to my second hometown, Los Angeles, to UCLA, where in the 1960s I did my doctorate in brain research. Although more than 40 years have passed, I feel strangely right at home. I meet the director of UCLA's Brain Mapping Center, a world leader in brain imaging, John Mazziotta. John, one of the most exciting things that brain scientists can do is to deal with the common things that we assume, like cognition and emotion. The imaging work that you have pioneered gives us new tools into assessing these kinds of functions.
You know, the areas where that's really interesting have been in emotions, decision making, social cognition, how people interact with one another. Those have really been quite remarkable. If you're exposed to something that you find enjoyable, and it doesn't matter what the stimulus is, it could be food, it could be art, it could be a political message, whatever. If it's a match with what you like or prefer, you have certain networks in the brain that become active. And if it isn't, then there are other networks that reflect your dislike for the situation. You can even use the same stimulus and take a person from one to the other. So if you feed them a food that they're very much enjoy, but you make them eat it until they're revolted by it, you see the whole transition in the same person with the same stimulus.
What are the structures? Is it just a certain pattern, or is
the cingulate in the brain seems to be very much a key player in this organization. It's right here.
Ah, okay, yeah.
Right above the white portion of the brain, the corpus callosum that connects the two hemispheres.
And in that area, you see activity when somebody likes something or doesn't like something, or both? Or?
Different parts of it will respond to different reactions. And that balance is, you know, part of your development, your past experiences, your cultural perspective. Great art in an Eastern culture may be very unappealing to someone from a Western culture, music, etc. So it's in context as well. And I think that's the exciting and frustrating part of all this.
The structures and networks of human thinking, energizing and pulsing in real time. What about emotion? Joy, excitement, anger, fear. How does the brain add feelings? So it's back to Manhattan, to NYU, this time to historic Washington Square. I'm taken by nostalgia. Almost 50 years ago, I had a hard year here, an undergraduate with a long commute and no high school diploma. Now I'm here to meet a leader in understanding the emotional brain. University professor in the Center for Neuroscience, Joseph LeDoux.
Very deep in the brain, as you said.
Joe, let's talk about the core of your research, which is the amygdala, this nucleus deep within the brain that you've shown is significant in the fear conditioning.
Well, so the thing to understand about the amygdala is that the reason it does what it does is simply because of its wiring. There's no mysticism about it at all. It's very, it receives inputs from the external world, from all the senses, and then it connects up to responses that control our bodily physiology and so forth. So we have outputs of the amygdala control blood pressure and heart rate, sweating, hormone secretions, all of the physiological signs that you have when you're highly emotionally aroused.
The fight or flight.
The fight or flight response, basically, yeah. And so those come out of this circular region here called the central nucleus of the amygdala. Mm-hmm. So that connects to the hypothalamus and to the brainstem and controls all of those responses.
How does it know in its original wiring that it should be a fear response as opposed to something else?
Right, so the amygdala doesn't know anything, right?
Right.
So it just gets electrical and chemical inputs.
Right.
The amygdala receives sensory information in its lateral nucleus, so that's the gateway in. So there's a lot of inhibitory neurotransmitters in that structure that prevent normal stimuli from activating it. The cerebral cortex out here is activated by everything, but the amygdala is activated by almost nothing. something has to open that gate. And there are two ways to open the gate. One is through genes or innate wiring that was put into the brain by evolution. So in the case of a rat, it's naturally afraid of a cat. In the case of people, we have innate fears of snakes and spiders because those were dangerous to our ancestors, and that's why those are common in phobias. So we have these innate forms of activation that open the gate because of wiring, and we also have learning. Learning allows stimuli to open the gate because of past experience. So the rat that's attacked by a cat along a certain path in the woods learns that that path is dangerous. So I think the amygdala example gives us a kind of template for then asking questions about other emotions.
How much of it, or how important are affective or emotional behaviors in terms of the totality of sentient life?
Well, affective, emotional behaviors are, essential to our entire being. We don't do anything that's not affective in one way or another. Those are the things that move us, and so we need to understand our emotions if we want to understand what it is to be human.
What feels so me, my feelings, is not so me. Emotions are a mechanism, localized in the brain, generated by the brain. Emotions are observable inside, testable, manipulable. But the brain is not like a computer, hardwired and fixed forever. The brain can change. It's shocking how much. I go to San Francisco to meet a world leader in brain plasticity, the changing brain. Michael Merzenich has pioneered cochlea implants, enabling profoundly deaf people to hear. But how could such crude devices work so wonderfully? The brain would have to give up a deep secret. Mike, you've pioneered this concept of neuroplasticity.
Yeah.
That is
Well,
a very critical understanding, because the old accepted wisdom is that the brain doesn't change.
yes, and I think it's been one of the most exciting things that's happened, is that we now have this completely different view of how the brain is operating. We now realize that the brain is actually remodeling itself, revising itself in detail. We understand that those changes are actually massive as we evolve in our abilities. Train an animal or train a human to do any new thing. Mm-hmm. Look in the brain as they improve, right? That's not a difficult experiment. It changes. It has a wonderful trick. It simply strengthens all of the connections in detail that contribute to a better try. Let's say I'm bouncing a ping pong ball on a paddle.
Right.
It's on a rubber band, and initially I might get a bounce or two, right?
Yeah.
But my brain knows what success is. It has a model of success. It's probably seen my brother or my nephew or somebody do it successfully, right? It knows what success is. And when it sees success, it rewards itself. And it rewards itself by releasing neurotransmitters that basically tell the brain, hey, save those connections. That was a good one, right? And through a series of, you could say, successive approximations, it saves those changes that result in a better and better performance. Ultimately, I master it. It's a wonderful trick to control your own plasticity, to control your own evolution. Historically in my laboratory, a research scientist working with me developed a cochlear implant, which is an artificial electrical stimulation device that gets implanted in the inner ear of a person that's profoundly deaf. The person hears nothing, and basically it is designed to shock the auditory nerve, to deliver input into the brain that can simulate the input that's normally delivered by speech, so that now oral speech, can be understood by the person again, so they can recover their speech and language.
That's absolutely remarkable.
They work. They're wonderful devices. Most people that receive them recover the ability to operate in language. And they can talk to you on the telephone, they can talk to you with their back turned to you. But my tiny point is that the information delivered by these devices is necessarily very crude.
Sure.
The normal input is very sophisticated, it's refined, it's elaborate, it's wonderful, right? Scientists for a long time looked at all of those details and imagined that all of those details really mattered. Now I take a device that shocks the auditory nerve. It's a little bit akin to playing Chopin with your forearms. I ask the person when the device is turned on, what do you hear? And they say, it sounds like crap, it sounds like noise, it sounds like somebody speaking a language that I've never heard before, it sounds like a robot, right? 3 or 4 or 5 or 6 or 7 or 8 months later, they hear everything. Now that's not a product of marvelous engineering. The benefits have to be attributed to the incredible power of the brain to adapt, to create a new construct of the details of language that's just as useful as the old one. How on earth can they have a unified, simple connection to all of that information? The only way you can account for it is if all of that resident information, all of that resident processing participated in the reconstruction of the new language representation. Just by such a manipulation, that is to say, by delivering into an inner ear information in a new form, I can come to powerful conclusions about how the brain organizes its activity. I know that it's using the incredibly powerful, you could say, top-down processes from all of the stored information to contribute to the organization of a new form of a decoder that takes this new trash and turns it into gold, and then connects it seamlessly to all of this information above it, right? And one other really interesting thing about these individuals is that when they recover their ability to understand what you say, they usually say, gee, Dr. Merzenich, it sounds just like it sounded when my hearing was intact. It sounds perfectly natural, right? Which is decisively and decidedly a trick of the brain. It's informing them the speech in very different form, encoded in a crude and radically different way, is perfectly natural. And that's the brain telling them that it's operational again.
That's incredible. That's something that I could have never predicted.
Yeah. Well, I didn't either. I didn't either.
Playing Chopin, say the etudes, with your forearms. A perfect analogy. Plasticity adapts the brain to its environment, even repairs brain damage. Remarkable, yes, but this I could always accept. But to restructure the nonsensical noise of artificial electrical impulses into the exquisitely fine structure of intelligible sounds astounds me. After a lifetime following brain research, I'm flabbergasted. What other mysteries does the brain hold? Brain hemispheres are vital for cognition. What about right and left brains? It's back down the coast to UCLA's Brain Research Institute, my alma mater, to meet a pioneer of split brain understanding. Eran Zaidel, originally from Israel, shatters our apparent unity of consciousness with brain-injured patients who act as if they know things which they vow they do not know. So we have the two sides of the brain, which most people see as the cerebral hemispheres. How can we begin to really get a sense of the structure of this duality?
The main point is that you have some kind of division of labor. What could that division of labor be? So perhaps for important computations, one side will compute while the other side will monitor, maybe compute another way. So one way to describe the division of labor between the two sides is to say that one side is top-down and one side is bottom-up. So when we perceive a forest, do we see the trees first and then those trees make up a forest, or do we see the forest first and then we see the trees? Turns out we do both. The standard view was that the left side is specialized for language, and the right side, at least in right-handed people, is specialized for space and attention. And that's generally true, but that doesn't capture everything. So you could talk about the perceptual style of the two sides, and it turns out that the left hemisphere is analytic and the right hemisphere is synthetic. Can you say a detail, can you embedded figure in a more complex design? That's what the left hemisphere is good at. It's not verbal, it's spatial, but the ability to see a detail in a more complex design is left hemispheric. On the other hand, the ability to complete a figure that's incomplete, to see things from unusual perspectives, unusual shading, unusual perspectives, is right hemispheric.
Is there creativity in that? Normally we say, the left side is more analytical and rational, and the right side is creative and expressive.
We do, and I think we are wrong. Creativity is the connection between the two.
Describe a split-brain patient.
That's interesting. In fact, if you see one of them walking around along the street, you wouldn't tell them apart from a normal person, which is amazing. You're cutting the largest fiber system in the brain, 200 million nerve fibers, and nothing seems to happen.
And you're doing that for...
alleviating intractable epilepsy.
Right.
When you actually test them in the laboratory, you see that there are many unusual things. You have two different people in the same brain. It's unbelievable.
What could that possibly mean, two separate people?
It means that we have two separate sensory systems, two separate perceptual apparati, two separate memory systems, language, personality, consciousness. So whatever else I'm going to say about consciousness, I'm saying it's dual. There are two of it. And that introduces a lot of interesting questions, of course, and introduces a lot of problems for religious people who believe in the unity of the will and of the self. The whole talk about consciousness in the hemispheres is very strange, right? Because you say, today the right hemisphere was very good, the left hemisphere was very obnoxious. You can ask them questions about themselves, and they have different views of themselves. And I believe that sometimes they are different even in the normal brain. So when I ask you, did you like the movie? And you say, I liked it and I didn't like it. Maybe what you meant was, I liked parts of it and I didn't like other parts of it. Okay, but maybe what you meant was, part of me liked it and part of me didn't like it.
That's a fundamental difference between the two answers.
Absolutely, absolutely. And it suggests that consciousness is not necessarily unified in the sense that it can have different representations at different times, even in the same brain.
So let's take some examples, some functional examples where we see the lateralization at work.
Right. When we have brain damage to the left side, people suffer major problems in language. Right side, they have a problem with space and attention. One disorder that's very dramatic is called hemi-neglect. When we have right parietal damage, patients have right parietal damage. They have a syndrome called neglect of the left half of space. So patients, very intelligent, verbal, ignore the left half of space. Sometimes the damage is large enough so he has a paralyzed left hand. He denies his illness. This has a term, anosognosia. He doesn't know that he has a deficit. So here's a disorder of consciousness, because he cannot do something and he doesn't know that he cannot do it. So he denies that this paralyzed hand is his own, gives it a name, Charlie. What do you mean Charlie? It's a hand. Yeah, it's a hand. Whose hand is it? Yours. Mine, it's connected to your body. I know, but it has a will of its own. And yet, here's another example showing the opposite in the same patient. He ignores the left half of space. You show him two pictures of a house, identical pictures. House, the same house below. The one difference is that the one at the bottom has some flames coming out from the left half. What do you see? A house. What do you see here? A house. What's the difference between them? None. Are they identical? Yes. Where would you rather live? The top one. Why? I don't know. Feels better. So here's a case where he does process the information in the neglected field, but he doesn't know that he does. So it's a lot of, significant, meaningful semantic information. Fire is bad and so on, but it's not penetrating consciousness, and yet it guides his behavior. So here's a good example of a dissociation between his knowledge and his ability.
And that reflects very definitely on the nature of consciousness.
Absolutely.
How does the human brain think and feel? How does it happen that 3 pounds of wet meat understands science, appreciates art, experiences love? Here's how to understand the brain. Specific brain structures, wired for specialized purposes, like the amygdala for fear. Specialized brain functions, which change over time through learning. Brain networks, waxing and waning, always dynamic.
That would be a wonderful experiment if I could.
Brain plasticity, the brain always reinventing itself. Dual cerebral hemispheres, left and right, with complex computational relationships. What, then, is human consciousness? Of only this be sure. Understanding the brain gets us closer to truth. But getting all the way to consciousness? Who knows?
For complete interviews and for further information, please visit closertotruth.com.